All right, 102 crew. Got a question from number 50 here. And let me just explain that this chapter is trying to introduce you to work and energy, and an extremely powerful and important concept in the field of science is that energy is conserved. The energy you start with is equal to the energy you end with. Now, it can change forms. So potential energy can become kinetic energy, or it can become heat energy. Probably should just mention those three for now. There's other energies, nuclear energy, solar energy, but really if we just start here in this chapter with kinetic energy, potential energy, and heat energy, we'll see here that we can do a lot of problems, and we can kind of understand what's going on based on the amount of energy. But this amount of energy is kind of like we saw with me making two columns for conservation of momentum. This is conservation of energy. And so when it comes to mechanics, there's three important conservational principles, and this is the second of the three we're going to see. The first one being conservation of momentum, and so I just kind of like to make two charts, and we did that in chapter 6, and so I'm kind of doing the same thing here for energy, and you're going to see that same thing with what we call angular momentum when we get into chapter 8, but let's not get ahead there. But those three conservational principles are three things that are very powerful tools when we deal with mechanics. So this is the second of our three conservational tools before we kind of leave mechanics and go into other physics here, so after chapter 8. But keeping that in mind, as I read this, it says a physics textbook is launched up a rough incline with a kinetic energy of 200 joules. Okay, so maybe if I, over here on this initial part, put something like this, kinetic energy initial plus potential energy initial, and I guess we have to have a reference, so I was going to put plus heat, but maybe I'll just leave that alone, equals then to later on the kinetic energy final, the potential energy final, plus anything that was now changed into heat energy. So again, this is what we mean by that conservation of energy. So looking at this one, they make it very clear that this number is 200, and all energies are measured in units of joules. Okay, so 200 joules. Now, potential energy, maybe I'll put it up here in this equation, is this mgh. That's the lab we were trying to demonstrate this week, as well as this chapter, that the potential energy is measured based upon its mass and its height, and of course the force of gravity, the g. So the mg is the weight, and then the height. Okay, but if we talk about this textbook maybe being at the bottom of the incline, because it says the physics textbook is launched up a rough incline, I guess I'm saying it has zero potential energy. So what this tells me is there is a total of 200, and that total doesn't change. So when it goes on to say here that when the textbooks comes to a momentary stop near the top of the incline, and so maybe I should kind of draw an incline. So it was down here, and its total energy is 200. And what I'm trying to say is when it gets up here to the top, it is still 200. It just may be in different forms. And the key to this problem says it, momentarily stops. And so when the book comes to a momentary rest, it's going to stop and then slide back down. But since kinetic energy, and maybe I'll put that one even higher up here, is 1/2 mv squared, when something comes to a momentary stop, we could say it has no kinetic energy at that moment. Okay? And so that's kind of the key step in this, what comes to a momentary stop. It has gained 180 joules of gravitational potential energy. All right, so they don't really say how high it goes, but they just tell me the overall energy is 180. And of course, there was rubbing going on, so there's some heat. And that's the magical step right there, is that would then tell you, because of conservation of energy, the heat must have a total of 20 joules. Okay, that way the total at this point is still 200. It's 180 in terms of its energy of its height. It's 0 in terms of its energy of motion. And it's 20 in terms of its heat. And all three of those energies have to add to our total of 200. Okay. All right, now if I keep reading this problem, it says, how much kinetic energy will it have when it returns back? And so it slides back down. And presumably, then we have another step of energy. Maybe I shouldn't have put final. That almost sounded like it was at the end. This is more in the intermediate. So maybe I should say, the energy at A, so down here on its way up. Then this is the energy at B, so it gets here to the B. Then it slides back down, so then it has energy at C. But again, at this point, I would do the same thing. There would be a kinetic energy, there would be a potential energy, and there would be a heat. And all of that, as they're saying, got to add up to 200. And I think what they're trying to imply all of this, because again, the question says, how much kinetic energy will it have when it returns back? So I'm going to leave that as a variable, kinetic energy, is we know it has gone back down to this 0 height, so it has 0 potential energy. We know it already created 20 on the way up. I think they're trying to imply that then sliding back down is going to make another 20. So that's how I'm going to put 40 here of joules for the total, okay? So that's why this first little calculation was important, saying, okay, how much energy was converted into heat? 20 on the way up and 20 on the way down. So keeping that in mind, when it gets back down to the bottom, it must have 160, right? So coming back down, so call this point C, it has 160 in terms of its kinetic energy. It has 0 in terms of its potential energy. And there's been rubbing both up and down. 20 then is created each way, so a total of 40 heat when it gets to the bottom. But that answers our question. But do you see how I use the conservation of energy, knowing that it always had to be that 200? And then we can answer the question, how much is it at the bottom? So conservation of energy, very, very useful, very, very powerful tool. Hopefully that helped.